Okay, so the first thing that we need to discuss in order to understand how we implement all these quantum information protocols in the lab is, well, how do we encode qubits in physical systems? So you remember qubits are nicely described by this Bloch sphere here. And so you, in general, you have a sort of, useful or more natural basis, which is the computational basis with a 0 and a 1. And then you have the superposition states, which are on the equator. And so here are a couple of examples how you can actually create qubits in the lab. Well, first with photons. And for instance, the polarization degree of freedom of single photons is really a qubit. So in this case, the 0 and 1 would be horizontally and vertically polarized photons. And then a superposition between the two, like this one here, would be a diagonally polarized photon. And then you have all the additional states, like the one here, for instance, the 0 minus 1, it would be, instead of being diagonal, you would be anti-diagonal. And then the eigenstates of sigma y, which would be here and there, these would be the circular left and circular right polarizations. Okay, so that is one possibility. With photons, there are other possibilities. You can also use the time degree of freedom or space degree of freedom. So photons are used a lot, in particular for communications, because when you have to send a qubit from one location to another one with a certain distance between them, then photons are very good carriers of quantum information. However, if you have to process information locally, for instance, like in a computer or something like this, then photons are not so good. First of all, they are not good because they travel very fast. So unless you have a good scheme to, slow the speed of photons, or then in general, photons are not good because yes, they will always travel. So what you could do is then you could map the quantum information carried by photons to atoms, for instance, to more generally solid state systems. And then, atoms, for instance, do not travel at the speed of light. And so if you think of an ion, you can trap an ion in an electromagnetic trap. And then these ions, you can isolate a single ion. And on these ions, you can also encode qubits, for instance, by using two energy levels. So typically the ground state and the first excited state. And then you can map the state of some light that would be resonant with this energy transition. So you can map your photon qubits to some atomic qubits. Okay, and then there is a final another possibility to create qubits, which is a bit more sophisticated. So these would not be really just a single particle or very elementary system. Would be a more complicated device. One example are the so-called superconducting qubits, which we see here. Good. So here you have an idea of what these are. So this would really be sort of little circuit that you can write in a superconducting material on some substrate. Okay, so this is really a system that has 10 to the 26 atoms in it. It's really almost a microscopic system, right? And what you do is in these circuits, you engineer something that you can really think of as electronic circuits, like the ones that are drawn here, okay? So here you have some capacitor, here you have an inductor. So this is an LC circuit, right? So it's essentially a harmonic oscillator. And if you quantize that system, well, then you have, so here you have the energy landscape of that system, right? So it's a harmonic oscillator with evenly spaced levels. So that system, it would not be very convenient to make a qubit because you see all these different levels, they are separated by the same energy gap. Oh, sorry. So if you think of manipulating the qubits here with light, typically, right, you will not be able to differentiate these two levels with respect to any other pair here, right? So then what you need to do is you need to make a perturbation to your harmonic oscillator to make it anharmonic. This is what you do here by adding this element here, which is a Josephson junction, I think. And so you see what then your harmonic potential now is changed here. And so now you see the frequency between the first two energy gaps is no longer the same as between these two here, right? So typically this gap if the oscillator is anharmonic, this gap will become smaller here, and therefore now you have a well defined and well separated in frequency qubit here, right? And these qubits you can now really manipulate, by adding phases, make them move on the Bloch sphere. And these are the kind of systems that that are used typically for making prototypes now of future quantum computers. So here on the right hand side you have sort of sketch of the architecture of these very basic quantum circuits that people are producing now. And okay, so you see there are lots of different elements, but essentially each of these circuits here would be one of these superconducting qubits. And then you see these things here, they are connected by long wires. And these are sort of resonators that enable to correlate these different qubits, right? So for instance, if you would like to apply some entangling operation between these two, for instance, a C0 gate or something like this, well, then you will have to use light here. So I think here it's typically in the microwave regime, and this light will sort of couple, will induce quantum correlations between these qubits, and then you can realize your different gates. So what people at Google now are doing, and many other places in the world, is really trying to make each one of these qubits here extremely good, right? Remember that at the end of the day, you want to make something that is robust to errors. So you should be able to implement some error correcting code. And this requires extremely high quality qubits here with fidelities of 99.9%. And then of course, you should have an architecture that allow you to have, millions or billions of these units here, and then be able to connect them and to, make them interact like transistors in a standard computer. All right, any questions so far? Don't hesitate to ask, because I might take huge jumps from what we've seen in the lecture and what I'm discussing now, but okay, you should react. All right, so this is for qubits. Now let's discuss channels. So here we're coming back to photons, basically, because channels we need when we want to send quantum information from one location to another one that is quite far. So of course, it's possible to send, in principle, photons via the air, right? But that is typically more challenging, right? Because, okay, if you think of our environment, I mean, in daylight, for instance, there are billions or trillions of photons moving around, right? So if you encode your polarization qubit on one photon and you want to send it from one location to another one, you know, in this huge ocean of photons, it's pretty challenging. And moreover, there are other challenges that will come back later, but somehow the most adequate and simplest solution is to use optical fibers. So optical fibers are just sort of, you know, two cylinders of silicium, right? That are, and so you have a core and another one that is a bit bigger around. Okay, like I don't know what's an example of something like this. Well, it's just a wire, right, with an inner part and an outer part. And so the point is that the inner part has a slightly higher refractive index, and so therefore light will be guided inside, right? So by now this is a technology that is incredibly developed, right? I think it was mainly in the 80s that this thing boomed really, and now there is an optical fiber connection in almost every house, right? So so it's something that you find everywhere. And so, okay, of course, usually optical fibers, they are used for classical communications, right? So information also arrives encoded in light. But there we talk about millions or billions of photons, right? So what we want to do here is very different because we just want to use single photons. But nevertheless, if you have a single photon at the right frequency, you can use optical fibers extremely well, right? So what you see here is this is the transmission loss with respect to frequency, right? Sorry, here is wavelengths of your light. And so you see typically in telecom, what people use, okay, you have all these different bands here, but the most important ones are this one here, the C band at 1550 nanometers, and this one, the O band, right? These peaks here, or you see the reason why you have these peaks in the transmission profile and why it goes up here is because inside the fiber, of course, there are some interactions between the atoms and the light. And so there are certain wavelengths that are more resonant with the structure of the atoms in the silicium, and therefore you have more losses there, right? So these different telecom bands, they are really the frequency or the wavelengths regimes where the transmission is best somehow. And so typically in classical communications over optical fibers, what you do is that you multiplex in frequency, right? So you can have many different channels. And for instance, even within the C band, I think you can have thousands of different channels, each one at a slightly different frequency, right? And then you can use a device to separate the light with respect to frequency, like a prism, right? And then you can access all the different bands. And so, of course, in quantum technologies, in particular for quantum key distribution, right, for quantum cryptography, well, the idea is to try to use these systems as much as possible, right? Because, you know, they have been developed for a long time, and the technology there, it works extremely well and is relatively cheap. And so here you see sort of, you get a better idea of the performance of the transmission over fibers. So in a sense, it's really outstanding, right? I didn't put the formula here, but essentially the transmission, the probability of transmission, it's something that is, you know, exponential. So it's a negative exponential in terms of the distance, right? So the transmission decreases exponentially, okay? And so if you would look at the transmission over 10 kilometers, I didn't put it here, I think it would be about 50%, okay? So this is quite amazing, right? Think about it, you input one photon in an optical fiber, 10 kilometers further, right? The probability that your photon comes out is 50%. Okay, something like this. Maybe it's 20%, sorry, but it's of this order of magnitude, right? So it's an extremely good transmission media, right? But of course, it's not perfect, right? And the reason why it's not perfect is because of these unavoidable scattering processes inside the fiber, right? So the interaction between the photons and the atoms, okay, this leads to these unavoidable losses. Now, because this is an exponential decay, right? If you go to 100 kilometers instead of 10, now the transmission drops down to 1%, okay? But 1%, it's still not too bad, right? So you can imagine working with something like this. If you would, however, go to 1,000 kilometers, well, then you see the transmission, it's essentially zero, right? So now you can wait for, you know, almost the age of the universe for your photon to come out after 1,000 kilometers. And so if you think about cryptography, right? This is something that you would like, so you would like to do cryptography between, I don't know, two users in the same city. So that is the range of 10 kilometers, maybe between two sort of neighboring cities. So that is 100 kilometers. So their QKD will work well. However, if you think of intercontinental communication, so there you are more like thousands of kilometers. Here here you are really limited, right? And okay, so this will also lead to me to tell you a bit about some other field of research which tries to boost somehow the length of quantum communications in order to go, you know, to have something that is where you can mediate quantum communication worldwide, let's say. Any questions here? Okay, good. Okay, so now let's move to something specific that we discussed in the lecture, maybe lecture 5 or 6, I don't remember. This is the Bell experiment, right? Related, so it's a test of Bell's inequality of quantum non-locality. And here, this is the famous experiment of Alain Aspect, conducted in the 1980s in Paris. And so here you see the experimental setup. So these are actually the drawings taken from the original paper. You know, by that time, people had to draw with pen and paper the figures they would put in the papers. You will see examples of, you know, more recent papers later where you have nice, you know, computer-made drawings, but here it's very primitive. Still, you understand the idea. So here we have the source, right, of our Bell experiment. Here we have Alice and Bob. And so you see here we have nu1, nu2. So these are frequencies. This is photon 1, right, going to Alice that has frequency nu1. photon 2 has frequency nu2. And here the point is that these two photons have entanglement in their polarizations, okay? And so to understand why that is the case, we need to understand how these two photons are created. And this is via some atomic cascade. So here you have the atomic structure of the medium here inside this source. And so the point is, you see, so here you have, let's say, the ground state. I'm not sure if it's the real ground state, but it's some level here. And so from this level that is well populated, if you can excite the atom to this higher level, and then, of course, the medium would like to relax, right? And the way to do so is via this double jump here, okay? So first you relax to this intermediate level that is metastable, right? And then you directly relax to the other one, right? And so you see in the process you emit one photon at frequency nu1 and another one at a slightly different frequency nu2. Okay, and because you can differentiate these two frequencies, you can send one photon on the left and the other one on the right. In fact, it might be that because of momentum conservation, one of these photons goes out on the left and the other one on the right, okay, because momentum has to be conserved. Okay, and now the point is that now you have two possibilities, right? So first, it can be that the first photon here is horizontally polarized, and then you can argue that there is no preferred direction in this system, right? So if the first photon is horizontal, then the second one should be vertical. Okay, so you will have a process whereby you have horizontal, vertical. However, you can also imagine the opposite process where you have vertical, horizontal. And then, because these two processes are indistinguishable, you will effectively create some entangled state between the polarization of each of these two photons, right? So you would have a state like horizontal, vertical, plus vertical, horizontal. So, this is really like a Bell state, right? But encoded in the polarization of these two photons. And so then what you have to do in your Bell experiment, right, is you have to make a measurement of the polarization in different bases. And so this is what you see here. So here, this little square here, this is a polarizer, right? And here you make a measurement of the polarization. If you want to polarize, the orientation of your polarizer is given by some vector A on the Bloch sphere, okay? And once you, so if your photon has that polarization, it will go through. If it's not, so if it's polarized in the orthogonal direction, it will go down here. So it's really like making a measurement of a qubit, right? So in a like a Pauli measurement. And so after you made this separation here, you still have to check where your photon is. So here you have to put a device to detect photons. So PM means photomultiplier. So it's a device where when you send a single photon on it, right, it's a little bit of energy that arrives in a medium. And if this medium is prepared in some sort of metastable state, the energy of one photon, which is arguably very little, is nevertheless enough to trigger some sort of cascade or avalanche in this device. And this leads to some electrical signal, which you can then measure here, right? And okay, so you see this sort of device here, which allows you to measure the polarization of your incoming photons. You have two of them, right? And so the idea here is that we want to have one measurement setting and another one, like in the CHSH inequality, right? We needed two different measurement settings. And we have the same on Bob, right? Exactly the same. And now you see there is this sort of weird arrangement here in the front, and the same here, right? And this is a device that is a switch. So the idea is that you want to be able to choose the measurement setting in a way, you know, that is completely separate and unknown to what's going on the other side, right? So remember that in order to test your Bell's inequality, you need, in principle, to put Alice and Bob in a space-like separated regime, right? So you need to be able to choose which measurement settings to perform. Is it A or A prime? And then you should be able to do essentially, so you should be able to make this choice before, almost before the photon has come out of the source, right? And so this was the real breakthrough in this experiment of Alain Aspect, that he was able to devise these switches here that were so fast that even though this whole experiment is on one table, so a 2-3 meter long table, right? Yet these switches were so fast that he could ensure space-like separation between Alice and Bob, right? And so that's why this experiment is very famous, because it's the first experiment that showed violation of Bell's inequality in a situation that is space-like separated, right? If it's not space-like separated, you can still think that there is some form of communication that is mediating the correlations. But if you are in a space-like separated situation, okay, then you can rule out any model where the communication is, you know, at the speed of light. Okay, you could still think of models where communication goes faster than light, but okay, then you go to really different physics. So here is the experiment that Alain Aspect was seeing. So here you see the horizontal axis is an angle. Maybe let me, so essentially what you see here is you see the, so I guess what is varied is the angle between these two polarization measurements. And you see that when you set the right angle, which is here, right? Then the vertical axis, so this S is just the CHSH expression as we saw it, right? Hello? Any question? Okay. So this vertical axis, this is the CHSH value. And remember that the bounds of this Bell expression are between 2 and -2, right? So anything between 2 and -2, you can explain in principle via some common cause model, right? Via local model. But if you're above 2, or as a matter of fact, also below -2 in these shaded regions, this is the non-local region, right? This is the point where your correlations are too strong to be explainable by any local model. And so you see these, so these are all the points measured in Alain Aspect's experiment. The line is a fit, right? So the predictions of quantum mechanics taking into account some of the imperfections of the experiment, and you see that it's very beautiful, right? It fits very well. And you have here points that are far in the non-local range, right? So this experiment it's really a landmark experiment. It's the first really convincing demonstration of quantum non-locality, right? Or violation of Bell's inequality in the lab. So it's really a pity that Einstein was no longer there to have seen this, but it's really a wonderful experiment. In fact, it's nominated every year since almost a decade for the Nobel Prize in Physics. So far, it didn't go there, but you know, who knows? Or of course, there are many like these, right? Many landmark experiments or theory results that are eventually waiting for a Nobel Prize, but okay, this is the lottery. All right. So here is something else. This is parametric down conversion. So this is like, let's say, the more modern way of creating entanglement in the lab. So in an space experiment, you had an atomic cascade. Now with parametric down conversion, the idea is a bit different. So you have some medium here, which is this yellow thing here. And this is a crystal. You see here it's BBO, some acronym for the exact composition of this this system. But what is interesting, what is going on in this crystal here is a nonlinear process of down conversion, right? And what happens here, so again, I'm sorry, I don't have the formula, would be useful, but I will explain it with words. So what happens in this crystal is that an incoming photon here, right, which comes from this, so here we have a UV laser pump, right, in the ultraviolet. So here you have sort of highly energetic photons that come in. And in this medium here, each of these photons has a probability, in fact, quite a low one, but let's say 10 to the minus 6, 10 to the minus 7, something like this. So this is the probability that one of the pump photons will be down converted to 2 photons. So one of them will go. Okay, sorry. Yeah, in fact, the 2 of them will go on this cone here. Okay. And the point is, each of these photons has, let's say, half the energy of the incoming one. Okay. So you need to conserve energy, right? That's why the outgoing photons, or the down converted photons, as we say, they have a lower energy, and the sum of these energies must be that of the incoming photon. You see, there is also an idea of momentum conservation, right? Because you see the momentum is this purple arrow here, and so the blue and red arrow, they are symmetric around it, right? So there is momentum conservation in this process. And so now, why does it create entanglement? Well, it creates entanglement because you have, oops, sorry. So you have here one cone here. So you see because of the geometry of the scheme, the photon, so one of the photons will necessarily be produced on this upper cone, right? And this is a photon that will be vertically polarized, right? And the other one will be horizontally polarized. And now the idea is that you see there are these 2 points here where the cones intersect. And so if you only collect light from these 2 places here, right? Well, then you end up with an entangled state in polarization, right? Because at this point, you see it could be that the second photon came from the upper cone, and that therefore the other photon here came from the lower cone, so you have a HV term. But of course, the opposite is also possible, right? And because these two possibilities are completely undistinguishable, well then quantum mechanics tells you that you have to add them. You see, like they becomes a coherent superposition of these two, okay? And here you see what this gives in the lab, right? So you see these cones, and here you see the intersection of the cones. So this is a system that you find almost in every lab now working on quantum information, and this is an extremely well-developed technology. All right, so let's discuss also a bit of the local milestone experiments. So you know, in GAP, in our physics department, quantum information is really a specialty, in particular in the groups of Nicolas Gisin and Hugo Zbinden. And so here, this is a very famous experiment that they did more than 20 years ago. And you see, the idea was to see whether these, quantum correlations, this quantum non-locality, was something you see that you could only see in the lab, like in Alain Aspec's experiment, where essentially there are 2 meters between Alice and Bob, or whether this is a phenomenon that you can really see on a long distance. Okay, so the question is, does this entanglement survive if you separate, let's say, the photons by 10 kilometers or something like this? And so that's why people here thought, okay, let's try to implement this test of quantum non-locality on, 2 really well-separated photons, right? So to do that, they used telecom fibers, right, to send the photons apart. In fact, they used the Swisscom fibers from the Swiss Telecom network. And so Brunner and Bellevue, for those who are not locals, there are 2 small villages around Geneva. And okay, they were chosen because they had a convenient Swisscom station where researcher could install a sort of temporary lab. And they have this nice separation of more than 10 kilometers, right? The source here, you see, this was, I believe, at GAP, which at that time was more or less where the physics building is now, right? So in the city center. And here you see the distance of these quantum channels, so these optical fibers between all these different stations. And so here you see the result of this experiment. So it's again shown as a sort of sine-shaped curve. But again, the important thing is the Bell violation, right? So this S is again the CHSH value. So the limit for local models is 2. And you see in this experiment, they had a very nice violation of this inequality, 2.4. And even with the error bars, it's still very convincing. Okay, so that was really an important experiment because it showed that these phenomena, they can really see them outside of the lab, right? It's something that is there on essentially long distances. So remember that, right, one of the deepest mysteries of physics is how do you move from the microscopic world where quantum mechanics is an incredibly good theory, right? It predicts things at amazing levels of precision, and quantum mechanics has essentially never been wrong in predicting experiments, at least in the low energy regime, right? So we have this very good theory, but quite mysterious also at the same time, theory of quantum mechanics. And then, of course, we have classical physics, right, which at our scale works extremely well. And so what is the transition from one to the other? We still don't know, right? If you want, the question is, what happens when you make a quantum measurement? Right? So from your quantum mechanics lecture, you remember, there is a collapse of the wave function. Okay, but what is that, right? So what does really happen there? And this we don't understand. So therefore, it's very interesting to test quantum mechanics, on larger objects, on larger scales, and see if eventually you find a sort of limitation, right? So if you can find a regime where the predictions of quantum mechanics are no longer observed, right? But so far, this has not been found. I'll come back to that a bit later, actually. So here is something more recent, so-called Bell experiments that can be done with ions. So here is the idea of the experiment. So here we have two ions that are, they are here, right? You see the ions, and these are trapped. Now the idea is that we are willing to make a Bell test between these two ions, right? However, these two ions, you see, they are separated by 20 meters, but in more recent experiments, these are separated by a kilometer, right? So they are really in two independent labs. So of course, these ions, they have never seen each other. So of course, they are not entangled, right? So the question is then, how do we entangle them? And I hope you remember the answer. Well, this is via entanglement swapping, right? So what you are going to do here is that you are going to manipulate this atom such that this atom will emit a photon, which you will collect here and then send into some optical fiber. And if you do the thing well, what will happen is that the polarization of this photon will be entangled, let's say, with the spin, some internal degree of freedom of the atom. So then you have, let's say you have a Bell state here between your traveling photon and your atom. You do the same thing here, right? So then you have two Bell states, right? And then in the middle, you combine them, you do a Bell state measurement, BSM, right? And this, okay, you can do here with your photons by sending them onto some beam splitter, right? So you have your two incoming photons, they arrive on a beam splitter, they will interfere actually on this beam splitter, and then you are going to just measure the polarization, okay? And if you do that right, you can actually project on a Bell state here in the middle, and that will then entangle your two distant atoms, right? So it's really entanglement swapping, teleportation of entanglement. And once you have that, well, then you can make a measurement of your spins here, of your atoms, and then you can also check for Bell inequality violation. For some reason, the results don't appear, so I think I'm using an old version of these slides. I'm actually sorry for that. These are not up to date, but okay. Well, the point is that this has been done. In fact, it has been done extremely well in 2015, but it had already been done before, already like in the early 2000s. In 2015, what was remarkable about these experiments was that these were so-called loophole-free tests of non-locality. So these were sort of the final experiments that really prove in the strongest possible sense that you have non-locality between between these two separated objects here. Okay. Any questions so far? Okay, good. Continue. So here is, we jump to something else. This is now cryptography. It's also a specialty of Geneva. And in fact, so you see along these first experiments on Bell's inequality, people here also developed other quantum information applications, in particular cryptography. And almost 20 years ago, they created a little company that is called ID Quantique, that is by now a pretty big company, still in Carouge. And this is the world leader now in this business of quantum cryptography. So here you see very primitive setup with Alice and Bob. And you see, so the idea is that in these devices you have lasers, polarizers, etc. And these are connected by some optical fiber here that is on this spool. Okay, and therefore you can, so if you have access to an optical fiber, you can really implement quantum cryptography with these sort of devices. And so these are all results, but that demonstrated, so these were also, I think, the first real world demonstrations of quantum cryptography. In particular, there was a nice one between Geneva and Lausanne using, you see, a optical fiber below at the bottom of the lake of Geneva here, right? And okay, so that showed that on a distance of about 60 kilometers, this technology works, right? You can really exchange a secret key. So as I said, this led to a company, which you see here, it was used in some World Cup football championship. It's also nowadays used by the local government in Geneva, and probably by different types of companies like banks. Whenever you have to secure communication over a distance of, let's say, no more than 100 kilometers, you know, if you really have to secure the data transmission, for instance, you know, if a bank has its headquarters and a data center that is typically placed in a different location, you really want to be sure that the communication between the two is secure, right? And so this technology here, I think today for 100,000 francs or something like this, you can buy a system. So it's, you know, for you and me, it's there is no point, right? But for a bank, 100,000 is not so much, and if it really secures your data transmission, it's really worth it. Okay, this is what you have in the devices. Okay, you see that it's complicated, has optics, electronics, and so on, but you see everything works nicely, and you can put it inside these boxes. Let's come back to research at university. So this is a result that I like quite a lot. It's by my colleagues from the group of Hugo Zbinden. You see it's 2018, it's just a couple of years old. And at that time, that was the world record of distance for quantum cryptography. And you see here it goes up to 400 kilometers. And what they used for this experiment, you know, to go that far, was they used this ULL fiber here. That means an ultra low loss fiber. You know, where you somehow you know, these are very expensive fibers, but you know, you can limit a little bit the effect of scattering and so on to increase the transmission. So they used that. And then you see also the other piece that is very important is they used here a device that is extremely good at detecting photons, right? So remember, the problem is that when you have such a long distance, once you send the photon in, the probability that it arrives it's very low, right? But then even if it arrives, you still need to detect it, right? And okay, detecting single photons is something that is typically challenging, and standard detectors have an efficiency of about 10% for doing this. And so what people here in Geneva developed to, overcome these limits is that they developed some device to detect photons that is based on a superconducting nanowire. Here is this structure that you see. So this is at, you see 0.8 Kelvin, so it's really cold. And so the idea is that this is a superconducting material that is, it's essentially at the, transition point between the superconducting phase and the normal conducting phase, right? It's just below the threshold. And so if you monitor the current that goes through this wire here, well, you should see that, in the normal regime, you see no resistance, right? Because you are still in the superconducting region. But when a photon comes, it essentially gives just a little bit of energy that is enough to break superconductivity and put your medium above threshold, right? And so once you see a resistance, it means that there was a photon that arrived. And it's amazing, with these devices, you can attain efficiencies higher than 90%. So 9 photons out of 10 you're able to detect with this device. So it's really amazing performance. And so here you see the results, like, so what you see here is the distance. So you see they reach like slightly over 400 kilometers. And here is the key rate. So admittedly, the key rate is low, right? So you see this is, so they are in the range of 10 bits per second. So it's really low, but okay, it still works, right? And you see, okay, so this is amazing, but this is in fact very close to essentially the absolute limit for this type of protocols. So in fact, if I remember correctly, these green triangles here, this is a simulation of the performance of a setup where everything is essentially ideal. So where this detector is ideal, where this fiber is really, essentially at the fundamental limit of these scattering processes, and where everything is really, optimized. And you see that this is the best possible performance you may ever obtain, right? So what they do here is almost there. But then, so these limits here also mean that if you want to go further, right? If you want to go, let's say, between different continents, and so you need something else, right? And so here is what you need. Well, you need the idea of quantum repeaters. So if you want to transmit information between A and D, well, then you see, if you try to do it directly between A and D, if the distance is, let's say, more than 500 or 1,000 kilometers, it doesn't work, right? You never get your photons out. So the idea of a quantum repeater is that you break the distance in several parts. So each part being at a reasonable distance, let's say 100 kilometers. And then between these parts, you have a so-called repeater. So you have a station here whereby you will relay the quantum information. Okay. So in fact, if you think of classical communication, we also use something like this, right? So if you think of these huge cables of optical fibers that go from Europe to the US, right? So they are at the bottom of the Atlantic Ocean. Every 200-300 kilometers, I think you have a station like this, which does something, however, much simpler, because it is just amplifying the signal, right? So in classical communications, you you say you could do like this. So if you want to encode a 0, you send light, so millions of photons. If you want to encode a 1, you send nothing, right? However, after some distance, your millions of photons, right, you have lost quite few of them, or in fact, maybe most of them. So at this point, you need to look at the signal, so you make a measurement, and if you find some light, okay, then you will re-amplify it, right? And this is not a problem to re-amplify light because you're just coding classical information. But of course, with quantum information, you cannot do that, right? Because if you would amplify a quantum signal, you would clone it, and this is not possible. So what these quantum repeaters do is something different, right? They sort of, you see, this is again some sort of entanglement teleportation, okay? And with that, you are able to boost your communication length to much longer distances. But of course, to make a system like this work, you need some solid state devices where you will be able to store the quantum information of your photons and then process it. So this is something that is still at the level of research. There is a lot of research on this, in particular at GAP also, but this is not yet commercial. And here on the right-hand side, you see another idea that, at first sight sounds completely crazy. It's the idea that instead of going, via fibers on the ground, you go via space, right? So if you have a satellite here, and you imagine you can communicate, you can make some exchange of key between this ground station and your satellite. Later, your satellite moves, right? And then you can exchange information with that station. So of course, with this, so you see, like if you have low orbit satellites, the distance here is about, okay, I don't know exactly, maybe, what is it, 100 kilometers or 200 kilometers? I don't know exactly, but it's in that range, right? It's not very far. In fact, it's only in the, you see close to ground level that you have still perturbations due to atmosphere, but at some point you are already outside the atmosphere. So there, the propagation of your light is much better. And so this looks like completely crazy, but turns out a couple of years ago, this was actually demonstrated in, well, not in the lab, obviously, but as a real experiment. In particular, this was done in China. So China develops a lot quantum information, like Southeast Asia in general. And so they managed to launch their own satellite, okay, dedicated to quantum communication and quantum experiments. And then they managed to do quantum cryptography between, okay, let's say Shanghai and Urumqi. Okay, so these are, well, so this doesn't correspond to this map, but just to say that they are, so if you know a bit about China, these are two cities in China that are very far apart, like few thousands of kilometers. And so they managed to do that and demonstrate that it works. And so you see, so the long-term vision of this research is that people want to develop a sort of quantum internet, so a network where the different nodes here are users, and so the users probably they hold some sort of solid state quantum system like trapped atoms, and then these nodes are connected by optical fibers, and so the quantum information can be exchanged between the nodes by using the photons and converted via processes similar to teleportation from atoms to photons. Okay, so here I have something about teleportation now. So this is in fact a sketch of the first teleportation experiment that was done in '98. Okay, I think I don't want to go into the details of that because it's sort of similar to things we discussed already. So maybe let me go forward. Okay, this is a nice teleportation experiment done, I think, yeah, more than 10 years ago, I would say. You see a pretty long distance. And this was done, in fact, in the Canary Islands. Maybe you recognize the name here, between La Palma and Tenerife. And so you see the point. So why are these places useful? It's because they are dedicated astronomical locations on these islands. They have good conditions to observe the stars and nice telescopes, therefore. So what people did here is to use these telescopes to distribute entanglement and to make a teleportation experiment between La Palma and Tenerife. Okay, and so here is essentially my last slide. So this is about something more fundamental. It's related to what I discussed before, namely the transition between quantum mechanics and classical physics. And so before I discussed some experiment where people are trying to test whether entanglement and quantum correlation survive on a long distance, and that turned out to be the case. And of course, another question is whether quantum effects survive or can be observed on larger and larger objects. Okay, so if you think what is the quintessential quantum experiment, it's single particle interference, right? It's the two-slit experiment. And so this is an experiment that was done with photons, with atoms, with neutrons, with ions. I mean, all that was done a long time ago. So we know that single quantum particles, well, they interfere with themselves, right? So you can take a photon, put it in a superposition, and when you have your two slits, each part of your superposition will explore one path, and then they will recombine and interfere. Sort of the best description we can give for this phenomenon, right? Now, the question is that going to happen with a cat, for instance, right? So if you have a cat and you throw it through a wall that has two slits, is it going to interfere with itself? Obviously, the answer is no, right? At least if you try to do the experiment at home, we'll never see the cat interfering with itself. But of course, the reason for that is that if you want to see this quantum effect, right, you should isolate your system from the environment. So if there is any information about the path, so-called witch path information that leaks out to the environment, this will destroy the interference, right? So of course, doing this experiment with quantum particles like photons or atoms is much easier than doing it with a cat because you can isolate them from the environment much better. But in principle, quantum mechanics doesn't say that it would be impossible to do this with a cat, right? If you isolate your system well enough, maybe you can throw a cat through two slits and the cat will interfere with itself. And so what people can do is, well, they cannot do with cats yet, obviously, but here you see a really beautiful experiment that is already quite old. It's more than, almost 20 years ago. So this is an experiment demonstrating the self-interference or the wave-particle duality of very big molecules. So C60, so you have 60 carbon atoms. These are the so-called buckyballs molecules, because they look like a football. And so here is the sketch of the experiment. So you have an oven to prepare a sort of stream of these molecules that come out here one at a time. here you have a diffraction grating. So these are your two slits if you want. And then here is a device in order to see where your particles arrive. And here are sort of the results, right? So you see clearly that there are these sort of interference patterns. It's a little bit different from the usual two-slit experiment. It's just the way this is done. But you see clearly that there are these peaks and that there are some oscillation and some nice interference. And so this is a group in Vienna that did this landmark experiment. I know that they could, a couple of years later, they could boost it to molecules that have thousands of, tens of thousands of atoms in them, right? So they are very big molecules, and still they could see wave-particle duality. And I think their next goal was to do this experiment with a virus. Of course, it's really a timely topic. So yeah, I don't know, maybe the coronavirus would be good for doing these wave-particle experiments. It's probably more useful in other experiments at the moment, but still, you see, the idea was to see if you can witness quantum effects on some system that is, okay, it's not quite alive, but you know, it's almost alive, right? You know, usually because a virus is, in a sense, not much bigger than these extremely big molecules that the people have looked at. But of course, the difficulty is that you need to be able to create a sort of train of viruses here, and then find a way to make a diffraction grating for this, and then detect them. So it's sophisticated but really beautiful physics, and yes, it's investigating one really of the deepest mysteries of modern physics. All right, so I think I'm at the end. Good. Yeah, so I hope you enjoyed this whole lecture. Also, I hope today you could see a bit how all these more abstract things turns out into more realistic perspectives, and how you can implement that in the lab. And yeah, that's it.